Thank you very much for introduction. Can you please raise your hands if you ever heard about Large Hadron Collider? Just to be clear. The Large Hadron Collider is a big machine located in Switzerland, in France, under the ground. No? Okay, who have ever heard about the Iron Man superhero from Marvel Universe movies? Okay, raise your hand if you're just shy and you don't want to raise your hand, even if you agree with the question. There will be a little link between these two parts. I really like particle accelerators, and I really like Marvel movies, and one of my favorites is Iron Man 2. In this movie, the superhero Iron Man faces a difficult challenge. His fusion reactor that provides energy for his iron suit faces a problem. The material of this fusion reactor starts to poison Tony Stark, and he will eventually die if he will not find a solution to this problem. For this specific fusion reactor, collecting of the dust is not a problem. So Tony Stark finds a solution. He obviously builds a small particle accelerator in his basement from a scrap material single-handedly in just 2 days. He creates a new material, he replaces the material of his reactor, saves himself, saves the whole universe, etc. I really like and I really hate this scene. I hate this scene because in Tony Stark movie, his particle accelerator was working from the first time. It worked on the first try, and it just doesn't happen in real life. I understand that there is aliens, magic, multi-universes in these movies, but this is just too much for me. But I really like this scene because probably for the first time I have... Hello, everybody. Probably for the first time I have seen a movie where particle accelerator is presented as a tool of creation, as something that can create new materials and help to solve our problems, and not as it usually is represented, where a crazy scientist build a huge machine, collide particles, the black hole appears, and we all die. What Tony Stark showed in his movie is much closer to reality, because with the help of particle accelerators, we can treat cancer patients with radiotherapy and proton therapy, where with a beam of protons we just burn the cancer tumor that is located inside the body of a human. We can also, with the help of synchrotrons, generate a powerful X-ray sources. Powerful X-ray sources, and look into the microscopic world of viruses and biological samples. And of course, at the Large Hadron Collider, we can study how our universe works at the smallest scales, and to study the laws of physics that were working at the beginning of our universe. But what is particle accelerator? Particle accelerator, it's not me, I'm sorry, it's doing it on its own. In particle accelerator, we accelerate charged particles, electrons, protons, or ions. We accelerate them to the speed, almost achieving the speed of light. And we need not just to accelerate one particle, but we need to accelerate billions and billions of this particle to achieve some useful effects. Despite the fact that particle accelerators is one of the most complex installations that are built by humans, the recipe for every particle accelerator is quite simple. We need just 4 ingredients. We need to generate our particles, we need to focus them, then we need to bend to the trajectory of these particles, and we need to accelerate them. To generate particles, we can with so-called injectors, where, for example, we have a Wolfram coil that is heating up, and with a thermal emission, electrons start to escape the coil and go into the accelerator, where they are accelerated by a ref cavity. Next, we need the bunch of particles can consist of the particles of the same charge, and the particles of the same charge like to repel from each other. In order to compensate this effect, we need to focus them with the magnets, so-called quadruple magnets. If we will use them in our system, the size of our bunch will be the same across the whole accelerator. But without these magnets, our bunch will be quickly destroyed, and probably particle accelerator will be damaged very soon. The next element is bending magnets, with which we can manipulate the trajectory of our bunch of particles, and we can even make the trajectory of this bunch circular, like in Large Hadron Collider. The higher the energy of these particles, if we want to increase the energy of these particles, we need either to increase the radius of the accelerator and make it huge like Large Hadron Collider, or we need to increase the magnetic field strength in the magnets. Of course, in this parameter, we have a certain limit. In this parameter, the only limit is our budget. But this formula is the reason why Large Hadron Collider is so big, because we have big energies and we have a limit on our magnetic field strengths in magnets that we use. And the last part of the accelerator that we need to apply to build this machine is accelerating cavity. Accelerating cavity is just a metal cavity in which we apply a RF power source, and we have a standing electromagnetic wave inside, and by passing this RF cavity, our bunch gets a little bit of energy on every turn, and it's becoming more and more energetic. Each of these parts is developed by a team of scientists that do not work. For example, the specialists on magnets usually know nothing about the accelerating cavities, and the specialists on injectors don't know about the whole machine. But somehow, by working together, these wonderful teams of scientists are able to create these wonderful machines. And with the help of these machines, we are able to achieve great scientific results. First of all, the particle accelerators is a basic machine for studying the matter and elementary particles. On this table, we can see the so-called standard model. Standard model is the most fundamental scientific theory that describes all the elementary particles that our universe consists of. And if you're not a specialist in particle physics, this table probably looks for you something like, the joke is killed, something like this, which is the same standard model but in Japanese. So the whole universe consists of these particles, but despite the fact that it is the most developed theory that exists nowadays, it doesn't answer all our questions. It doesn't answer the question where the universe comes from, why this standard model is exactly like it is, what is dark matter, what is dark energy. And in order to answer these questions, we have basically two strategies. We can increase the energy of collisions between our particles, hoping that we will discover some new particles that is not in a standard model. for this, we need to build big, huge machines. And another strategy is increasing of precision of our measurements. So we can build a machine that is much smaller, but it's working in a very specific energy region, but is working with a much higher precision than Large Hadron Collider. For the first strategy, there are several projects. The most famous one, probably, a Future Circle Collider that is going to build, that is planned to build in France as the next step of Large Hadron Collider. It is going to be a collider with 100 kilometers circumference. Another project is circular electron-positron collider that are planned to build in China. The length is the same, so it's very interesting to see which of these projects will be realized first. But if you think that 100 kilometers is ambitious projects, probably with a budget of $20 billion, there is also a project of building a very large hadron collider on the moon. Maybe we will need like technical pass for fixing this stuff, or as you say, or I just continue. I don't know. I think it's just annoying. It's like a little.
Actually, I'm sorry, just this technical issue. This problem with the project causes by the plugs. If anyone is using the plug on the table, please take it off, because it.
You know, me and Yaroslav Sadovsky, we are scientists who can build complex machines such as particle accelerators and thermonuclear fusion reactors, but projectors is something else, like printers. They are working on their own laws. So, probably it will be harder to imagine a project that is more ambitious than the project of building a very large hadron collider on the moon. Of course, it's more like intellectual challenge than a real project, but maybe our grandsons will be able to realize this project. And idea of the project is very simple. You need, in order for a large hadron collider to work, you need to cool down it to very low temperatures. And it is very low temperature on a moon, so you don't need to spend any additional energy for cooling. About the small projects, I can say about one example. This is a muon G-2 project in Fermilab in the United States. They have this very specific task of measuring magnetic moment of a muon. And this is an interesting project because, in theory, the value of this magnetic moment should be like this, and an experiment like this. And everything agrees very nicely until you go to the 10th digits. For ordinary citizens, there is not so much difference in these two numbers. But for a real scientist, he understands that there can be two explanations. It's either we don't know anything about muon magnetic moment, or there can be new particles that affect this muon magnetic moment. And it's probably the biggest scientific achievement of this year. Nevertheless, I'm really excited about the results because they were able to achieve the very high precision of these measurements. Also, there are two small colliders that are built in Russia currently. This is like Small Hadron Collider, nucleotron-based ion collider facility NICA in Dubna, and Supercharm Tau factory that are probably going to be built in Sarov. Both of these machines are much smaller in case, but they are aimed at a very specific task. And probably here we will find some physics beyond standard model. And it will be a Nobel Prize scale discoveries. So about the radiotherapy, another application practical of accelerators is radiotherapy. With a small accelerator, we can accelerate electrons to a high speed. After that, this beam goes into the target, generates a lot of X-ray X-rays, and with the help of these X-rays, we're starting to damage the tumor, the cancer tumor of the patient. Because of this radiation, we damage the DNA of the tumor, and it eventually dies, and the patient lives. Another technology for cancer treatment is proton therapy. Here, with the help of proton beam, we can destroy the tumor that is located inside a body just by burning it by millimeter. And we also have this technology here in Obninsk in one of the medical centers. The last but not the least application is the synchrotron sources. Electrons have a very interesting effects when they reach relativistic velocities and they go in circles on the orbit of accelerator. It starts to emit synchrotron radiation. And interesting thing about this synchrotron radiation is that it's also in X-ray diapason. And the wavelength of X-ray is compatible with the size of an atom. And because of it, we can, with these X-rays, get a very clear pictures of proteins, viruses, and with this knowledge, we can create new medicines and again, treat illnesses. And another interesting application of these X-ray sources is cultural heritage research. Here we have a scroll from that was burned in the city of Pompeii due to eruption of Vesuvius volcano, and it's absolutely burned. You cannot unscroll it, you cannot read what's inside of it. But the ink that was used for scribing on this scroll contains a little bit of particles of metal. And by scanning with X-ray this scroll, we can create a 3D map of distribution of this map of this metal that contains an ink, and we can unscroll it with the help of 3D models like it's presented here. Synchrotron radiation sources have a lot of applications, and currently in Russia there is 4 synchrotron lasers are built, one in Moscow, one in Protvino, which is just 30 kilometers away from here, and another one in Novosibirsk, and another one in Vladivostok on Russky Island. This is not a full list of all the mega science projects that are currently built in Russia, but I have no any doubts that the researches that will be achieved on this machine, even the Tony Stark will be quite jealous of these achievements. Thank you.
Thank you very much, Yaroslav.